Hello everyone, I am Mrs. Priyanka S, Assistant Professor, Department of Electronics and Telecommunication Engineering, Walchand Institute of Technology, Solapur. Today we are going to learn about the root locus method. These are the learning outcomes. At the end of this session, students will be able to learn rules of the root locus method and also draw the root locus and understand their applications. These are the contents: introduction, importance, rules for root locus construction, key properties, applications, and conclusions. Now take a pause and recall the stability of the system. We have already discussed in the previous lecture about the stability of the system. The system reaches to the steady state value, then we are going to calculate the stability of the system. We have already discussed the two methods, that is Hurwitz criteria and the Rouse criteria. Now today we are going to learn the third method, that is the root locus method. Now introduction. Root locus is a graphical method for examining how roots of the system change with the variation in the system parameter. So in this method, movement of the poles in the S-plane is sketched when a particular parameter of system is varied from 0 to infinity. It helps in studying the stability and transient response of the control system. Second, importance. It provides insight into the system stability. It also helps to design controls by adjusting the gain. It simplifies analysis of higher order systems, and it used to predict a system behavior without solving equations repeatedly, because in the previous method we have used the equations. Okay, so that will be overcome in this method. The basic concept about the root locus. Here we have to consider the characteristics equation 1 plus g of s h of s equal to 0. For the root locus, k is assumed to be a variable parameter and it is a part of a closed loop system. So here we are going to consider g of s is equal to k into g dash of s. So if we put g of s value in above equation, so characteristics equation will become 1 plus k g dash of s h of s equal to 0. So here the closed loop poles, that is the roots of above equation, are depend upon this k value. Now if k is varied from minus infinity to infinity, we will get separate set of root of characteristics equation. So if all such locations are joined, we will get the root locus. If k is varied from 0 to infinity, it's called direct root locus. When k is varied from minus infinity to 0, it is called as a inverse root locus. Now there are the rules for drawing the root locus. So rule number 1, the root locus is always symmetrical about the axis. Roots of this characteristics equation either real or complex conjugate or combination of the both. So from the transfer function we are going to calculate first poles and 0. So here rule 2, p is the number of poles and z is the number of zeros. So for that, here two cases are there. If p is greater than z, then number of branches is equal to number of poles. So branch will start from each location of open loop poles and it will terminate at the open loop 0. So the remaining branches will be approaches to the infinity. In the second case, z is greater than p. So here number of branches is equal to number of zeros. So number of branches starts from location of poles and terminate at 0, while remaining originates from infinity and approaches towards the 0. So this is the difference between p is greater than 0, z, and z is greater than p. So here we are going to calculate the number of branches for the root locus. Now in the rule 3, the point on real axis lies on a root locus if sum of number of open loop poles and open loop zeros on real axis to the right side of this point is odd. So where the root locus occur, that we will calculate in rule number 3. For example, this is the transfer function in which we have two zeros, so that will be calculated by s plus 1 and s plus 4, and from the denominator equation we are going to calculate the poles. So two zeros, s is equal to minus 1 and s is equal to minus 4. It is represented by the circle. And the poles, there are three poles, s is equal to 0, S is equal to minus 3 and S is equal to minus 5. So here we have a 3 poles. Now here we are considering the point P, whether it is lying on a root locus or not. So to the right side of this P, there is a 1, 0 and 1 pole. So its addition is what? 2. So addition is even, so that's why no root locus occur in between minus 1 and minus 3. For the Q point, if we consider right side of the Q point, there are 2 poles, 0 and minus 3 and 1, 0, that is the minus 1. So here addition is 3, that is odd. So here root locus will be there in between minus 3 and minus 4. Now for the point R, to the right side of the R, we can say that here 3 poles are there and 0 is there. So no root locus will be there. So in the second diagram, we have written here the root locus will be there in between the minus 3 and minus 4. Here no root locus is there, no root locus is there. So in this way we are going to plot the poles and zeros. Rule 4, here if number of poles are greater than number of 0, so number of branches approaches towards the infinity. So here we are going to calculate the branches, okay, that branches approaches to the infinity along a straight line, that are called as the asymptotes. Okay. Now these asymptotes are always located about the real axis. So for drawing the asymptotes, we should have the angle theta. So it will be calculated with this formula. So where Q is 0, 1, comma 2 up to the P minus Z minus 1. So with the help of this angle, we can draw the asymptotes. Rule 5. All the asymptotes intersect the real axis at a common point known as a centroid, denoted by the sigma. The coordinate of centroid can be calculated as, this is the formula for calculating the centroid. So here we have to consider the real parts of the poles, summation of real parts of the poles minus summation of real parts of 0 divided by P minus Z. So from this centroid, we are going to draw the asymptotes with the angle. Rule number 6, there is a breakaway point. It is a point on a root locus where multiple roots of the characteristics equation occurs for a particular value of a k. So breakaway and break-in points occur on the real axis only. Breakaway point will be exist where the root locus will be there. Okay. Now there are 3 predictions for the breakaway point. Prediction number 1, if there are 2 adjacently placed poles such that 0 and minus 2 for this example on real axis, in between them, if it is a part of a root locus, then there exists minimum 1 breakaway point in between adjacently poles. Okay. So here to the right side of this, only 1 pole is there. To the right side of this point, only 1 pole is there. So summation of the poles and 0 is odd. So root locus will be lying here and the breakaway point will be there in between 0 and minus 2. The prediction 2, in the prediction 2, if there are 2 adjacently placed zeros and on a real axis, in between them is a part of the root locus, then there exists a minimum 1 breakaway point in between adjacently placed zeros. So here we can say that to the right side of this minus 2, 1 0 is there and 2 poles are there. So addition will be odd. So root locus will be there in minus 2 and minus 4 and there is a breakaway point. Prediction number 3, if there is a 0 on a real axis, to the left of that 0 there is a no pole on a 0 existing on the real axis. So here we can say that to the right side of this there are 2 zeros and 1 pole, 3 poles. So addition will be odd. So root locus exists here and the breakaway point will be there. Okay. But condition is that here after this 0 there should not be any 0 and any pole. So these are the 3 predictions for the breakaway point. Then the rule number 7. Here we are going to calculate the intersection point with the imaginary axis. Okay, when we draw the root locus. So here are the some steps for calculating the imaginary axis intersection point. Here consider characteristics equation this 1 plus g of s h of s equal to 0. Now from that equation we have to calculate the Routh array in terms of the k. Then we have to determine the k marginal, that is value of k, which creates one of the row of Routh's array as a row of except the row of s to the power 0. So here we have to construct the auxiliary equation above that 0 row by using the coefficient row which is just above the row of zeros. After that, roots of auxiliary equation at k equal to k marginal are nothing but the intersection points of the root locus with the imaginary axis. Now rule number 8, angle of departure. So in the angle of departure, as a branch always leaves from the open loop pole, it is advantageous to know that at what angle it departs from complex conjugate poles. So this angle at which it departs from the complex pole is called as the angle of departure. So this rule is applicable only when the complex poles will be there. So this is the formula for calculating the phi d 180 degree minus phi, okay, where phi we are going to calculate with the help of this formula, summation of phi p and summation of phi z. So here where summation of phi p, it contributes by the angles made by the remaining open loop poles at the poles at which phi d is to be located. And similarly phi z, it will be contribution by the angles made by the open loop zeros at the pole at which phi d to be calculated. Then next one is the angle of arrival. This angle of arrival can be calculated with the help of the following formula. So these branches will arrive and terminate at the complex zeros running tangentially to the lines whose angle are given by the below formula. So phi a is equal to 180 degree plus phi. Now in this way we are going to calculate the root locus. These are some key properties. That is, it is always symmetric about the real axis. Root locus is asymptotes defined by this formula. Centroid will be calculated with the help of this formula, summation of poles minus summation of 0 upon p minus z. Breakaway and break-in points found by solving dk by ds by taking the derivative equal to 0, and then angle criteria used to check point validity on a root locus. These are the application. Stability analysis of control system we can calculate. Then controller can be designed, that is such like a PID, lead lag compensator. Performance improvement in terms of overshoot settling time. It is widely used in electrical, mechanical and aerospace system. These are the conclusion. Root locus is powerful tool in control system design. So it provides a clear visual representation of pole movement, useful for ensuring stability and desired performance. And it is simple yet to effective method introduced by the Evans. Okay. Thank you.